Okay, now that the solution is done, first let's look at our how the shaft is getting deflected. So I can show you the deform and undeformed shaft here. After that, to double check our accuracy of our model and see everything is good, I'm gonna show you guys ANSYS has found reaction forces at the bearings left and right. So I want to compare it with our hand calculation. So let me see where that was. It's gonna be here, list results, reaction solution, you see here, and then I say all items. And if you remember, we had node number 1 on the left side, left bearing, and node number 11, the right bearing. So, and also if you recall, we had, let me open my notes again. So page 94, I think it was. No, a bit above. Okay, let me go up. So using the loads on the gears, which was given in the problem statement, you guys can find reaction forces at the bearings, right? So you can do that by manually by using equations of equilibrium. So if you remember, we had a reactions equal to at node 1 357 and 115, and then on the 11, the right bearing, we had 725 and 1776. So let's look at my results here. On the left bearing, which is node 1, you see fx is 0, fy was my reaction in y direction, which is 0.356. Remember, my unit in the ANSYS model was kilopounds, so this is basically 357. fc is 115. I have moment in x, which is technically 0. So at node 11, I'm sorry, my forces in y direction 725 and fz is 1776. These are the exact numbers we had, if you remember, from the hand calculation. So alright, so this is kind of reassuring for us that our model is doing, is right. So next I'm gonna look at my, our slope and deflections, right? So you come here, nodal solution, and I click on here DOF solution, and this is gonna give us the solution, nodal solution. In other words, it gives us displacement of each node in x component of it in x direction, y direction, z direction, and this one is going to give me displacement of that. It means the vector sum of those three displacements, and the other three, the second three, you see, after that the three items you see rotations, these are slopes, and this last one is actually vector sum of slopes. So we are going to look at our key element and compare our displacement here, deflection with ANSYS, and hand calculation. Okay, so let's first look at our displacements, and this is going to show me all displacement for all nodes. Okay, so node 1 was my bearing again, node 11 was my other bearing, left and right. And other node which is important for me is node 4, which is center of one of my gears, and node 8 was the center of the other gear. So let me open your book and take a look at the you know, those numbers from book. I have Shikley's book, so let me again go back to this shaft. Okay, so alright, if you look at the solution of the example, yeah, so this is what they have here. If you remember, I said that we have moments in two planes acting on two planes, xy plane and xz plane. So xy plane, you're gonna have a moment diagram and shear force diagram, which I have reviewed that for you before. And then you see on that plane I'm gonna have a deflection in inch and a slope in that plane, on that plane in degrees. So similarly for xz plane, you have your moment diagram, shear force diagram, you're gonna have deflection and you're gonna have slope for I apologize for deflection and a slope for that plane, and your total displacement and total slope are going to be vectors of these two. Alright, so we have this table, your book summarizing slope and displacement at critical elements, critical components. For the left gear, you guys see the deflection is on xz plane is this much, xy plane this much, and my total, which is the more important value, is, let's see, for left gear is 0.00091, or actually 3 zeros and 92. Okay, so let's see what I have here. That is my in my model. Okay, let me see. Okay, yeah, I'm sorry, I was looking at the gear. So left gear, it means that I have to compare that number with node 4. Node 4 was the center of my my gear. So I have here, you guys see, I have 0.00098, right? So what I have here is 0.00092. So the results are comparable. So the model they have here is different from what I have. They have made more simplifying assumptions. Alright, so this number is very close to mine. And then let's look at the right gear deflection. The book has 0.0017. Okay, so let's see what I have. That's gonna be node 8, right? So I have 0.0019. So if I wanna round it, I have actually 0.002, and he has almost that, 0.02. So they are acceptable, they are close to each other. So now let's look at the slopes for bearing, left bearing, which is my node 1. You see that the book has 0.00030 and 5, and let's see what I have there. We are looking at the deflections right now, so I come here, see the rotation vector sum. So node 1 I have, you see here, I have very close numbers. So node 1 rotation in total rotation, what I have is 0.0005. So, and this is what he has also, 0.0005, right? And the right bearing slope, he has, that one is large, no, it's actually, yeah, it's larger, 0.0011 actually, 0.0011. Let me see what I have on my last one. This is my last one, is 0.0011, right? So you see that one is matching with what he has. and left geared slope and right gear slope. So if you remember, they were node 4 and 8. So let's look at the slope here. Node 4, I have here point, I have what? 0.0004, and he had the same thing, right? 0.000414. I had 427, but they are very close. Number 8, I have same thing, 0.0041, and he has 0.00042. So you guys see that my results are pretty much very close to what book has. So he says that he has used a simple planar beam analysis program to find these, and you can do this actually manually by hand. So but you learned in 309 how to find deflections and a slope when bending moment diagram is given, right? But the problem is here, as I said, the shaft diameter is changing, and also shaft diameter is changing, and you have to find deflection on that plane, xz, xy, and xz, and then do vector sum. So by hand it's gonna be a lot of work. Alright, but he says that he has used a program, but he does not say what program. But now that you guys have access to ANSYS, and you see this is how you can analyze a shaft. So to find deflection, you see I used a linear model, a wireframe. If I want to do this thing myself, I try to explain it all the details, but if you do this a few times, and doing it for a new shaft is not gonna take really a long time. So alright, so I hope you guys find it useful, and alright, so okay, that's about it. I'm gonna close this file now.